All right, I think we can begin with today's webinar. Hello and welcome everyone. My name is Adrian Kramer. I'm one of the application engineers here at Diabatics. And in today's webinar, we'll be covering multi-objective optimization for battery cold plates. And also I will be covering how generative design can cut your manual engineering hours to only a few minutes. So to provide you with a quick agenda on what we will be covering today, first, I'm going to give you a technical background on setting up multi-objective optimizations. Then I will actually do a case setup start to finish on ColdStream for this very cold plate that we're optimizing. I will do a results presentation of the cold plate, of which you already get to see a sneak peek here. Then we'll have time for some questions. And at the end of the webinar, I'll provide you with some information on how you can get started with generative design already today and how to stay in touch with us. All right, so to begin with the technical background, so in any multi-objective optimization, of course, the first thing you need is an objective function. And how this objective function differs from a single objective is the fact that we have several parameters that we're optimizing for, and with that comes the introduction of these weighting factors. So this W you see here. And so why is this actually important for battery cold plates in electric vehicles? Well, for battery cold plates, there are several parameters that play a key role in the performance of the battery cold plate, such as a low global temperature variance across the entire plate, pressure drop, for example, and also the manufacturing constraints. So we will be optimizing for all of those parameters in this multi-objective optimization using generative design on ColdStream. So with this objective function, of course, then you have a set of hard constraints that go along with it. That's just the general definition of such an optimization. Then to make it more specific, well, let's start off with defining it for just a single objective. So in this case, we are minimizing temperature, taking the integral of temperature over a certain domain, and then we have fixed value constraints, these hard constraints that you see down here for the temperature spread, for the pressure drop, and for the manufacturing constraints. But with multi-objective, what you can actually do is translate some of these hard constraints into a further objective. So now we're looking at the multi-objective statement, where we are not only optimizing for a low global temperature, which is the first one here, but also for the temperature variance here. So now we have two weighting factors, W1 and 2, and these weighting factors can actually be clearly identified in ColdStream, and I will show you that once we get to the platform. And then including with these objective statements, you also have fixed value constraints. And so setting objectives, you always have to keep in mind, what am I minimizing for and what are fixed value constraints, to basically group them into these two groups. All right, and so why is an efficient cooling system in an electric vehicle actually important? Well, all the autonomous control systems, they rely on the battery itself. Of course, the battery lifetime and battery health is very directly linked to a well-performing cooling system, as well as the charging time. And of course, you want reasonable production costs, which is why the manufacturing constraints are so important. And so, say you have a certain design challenge. The conventional way of tackling this is by creating an initial CAD model. The design engineer draws this. They hand it over to the CFD expert. They do a performance simulation. You analyze the performance of that, and then you do an iterative trial and error process, a cyclical process, until you draw the design that actually meets all the requirements that you seek. However, what is special about generative design is that it streamlines the cyclical trial and error process in the conventional design method that is now streamlined into a linear process, so that if you have good input data for the design challenge at hand, you only have to set up the problem statement once, and the optimizer will compare hundreds of different designs until it gets to a optimal performing one. And that's what's special about generative design. It can address multiple objectives with only one case setup, and the days of this trial and error process of CADing and simulating, those days are over. They're all housed within the generative design software itself. And so here you can see, all right, a conventional solution is, for example, a serpentine shape, while a generative design technology will give you these optimized, these organic shapes and structures. And so ColdStream is the generative design software that we have at Diabatics have created, and it specializes in topology optimization for both thermal and flow. And so to do a case setup in ColdStream, you have to keep these steps in mind. So firstly, you always have to upload your CAD geometry. That is a given. Then you set your solids and your fluids. You define the boundary conditions for thermal and flow. And then you have to set a certain target objective. And here, the design space that you define in the CAD preparation is quite important, and you'll see that on the platform. But essentially, the design space is where you give the generative design software the freedom to make the choices. Do I place structures there or not? And then the second part of, well, I should say for the design region as well, you also specify those manufacturing constraints. So most cold plates are either sheet metal formed or roll bonded, and all of those inputs can be added on the generative design platform ColdStream as well. And then the last target definition are those multi-objectives that we discussed. So setting a target for a temperature minimization, a target for temperature variance minimization, and also for a fixed value constraint for the pressure. And then lastly, the output that you get out of ColdStream is actually a step file of the heatsink itself, or of the structures, of the optimized structures that ColdStream has generated. All right, I shall switch to the platform now, so give me 1 second. All right, fantastic. So I hope, well, ColdStream is now visible. And essentially the first step of uploading the geometry was already performed. So you can see the cold plate right here. We don't actually have to model the full vehicle, only the plate itself. And just for context, again, we have 4 different battery modules that are in this case modeled as surface patches. We have an inlet on one side, an outlet on the other, and then a base and a stamped plate. So also the battery packs don't have to actually be modeled, those can just be surface patches. So to start your case setup, you define all your solids first. So let's start with the base plate. Here you would just simply define it as a solid. You can always choose to rename it. You select a material, for example, aluminium in this case. So we have a materials library readily available, but if you need to add a custom material, as long as you know the properties, it's as easy as implementing it here. And then it's always part of your user library. And then for every solid, there are a few more options you can always enable. For example, the effects of radiation, that was not needed in this case. You can always add a heat source to any of the parts, but we modeled the batteries with surface patches, so I'll be inputting the heat load in a second. You can enable rotation, again not needed, and you can always add a target definition to any of these parts. All right, moving on. The other solid is just the stamped plate, in this case here on the bottom side, and as you can see, those are filled out quite similarly as the base plate over here. Then you need to define the fluid region. So actually in your CAD preparation before uploading a part to ColdStream, you basically need to create a fluid volume. So whether that's an air volume or a water glycol mixture, any sort of coolant, whether it's air or liquid cooled, it's entirely possible to accommodate for. But you do need to define this fluid region prior to the import into ColdStream. All right, so then the definition of the fluid region is actually quite similar as to the solid. You just then click here on fluid. Again, you can rename it. You select the material. So now you're in our fluids library where you can see, for example, we have air, even temperature dependent properties, and then any sort of coolant or fluid that you might be working with. Again, you can add it to your custom library. Okay, you can always enable the effects of buoyancy in case you have natural convection cases. That was not needed here. And then for the flow behavior, you do have to define a turbulence model. In this case, K omega SST was selected. We have a really great documentation page in case you're not so familiar with fluid mechanics. You can look up a little guide on which one to select right here. So in our case, we selected K omega SST, and the remaining selections were just left blank. All right, so then in the next step, let's define our boundary conditions for the flow behavior. So I hope you can all see it. The inlet is right here. And so that's just modeled with a surface patch. Same with the outlet on the other side. And so for inlets, typically those are defined with fixed flow rate inlets. You can also use fans and pumps as part of your user library. So if you know, for example, the performance curve of those, you can add those. In this case, I defined it with a fixed flow rate inlet, more specifically a volumetric flow rate. You have the option to include velocity or mass flow rate, not a problem, and you impose those here. For the outlet, 9 out of 10 times, it's just a pressure outlet with 0 Pascal. Okay, next are our boundary conditions for thermal. So here, like I already mentioned, the 4 battery modules, they were modeled as a group of surface patches. Now you can have as many as you want there. We just decided to do it this way because we knew the total heat load of the overall 4 battery modules together. So for these boundary settings, you would select a heated wall. You can also work with fixed temperature walls, or if you just have external or insulated walls, you select them there. And then here you input your heat load. All right, we'll come to the target setting lastly. I think next I would like to show you the design region, because I think this is quite important and also where it gets interesting. So your design region always needs to be a sub-region of the fluid itself. So as you can see here in this olive color, that is sitting inside the coolant region. And the biggest difference is that the inlets and outlets and the sections where you allow the flow to develop, those are not included. And that basically means the optimizer, so ColdStream, is not allowed to place any structures there. So actually what happens when you submit a case to ColdStream? So this empty design region is then filled with an initial best guess of structures to guide the cooling channels. That first design iteration is then backed with a CFD performance to evaluate the thermal and flow performance of the initial design. The optimizer will then decide where to take the design next and generate another design that is again evaluated with the CFD simulations. And in a machine learning algorithm, it knows where to take the design next to get to a better performing result. And after comparing hundreds of different design iterations, you get to a most optimum performing design. So that's really the magic of generative design, that you have a smart algorithm deciding how to create the design itself. And that is the basis of our software ColdStream as well. All right, so how do you define this design region? Well, for a subregion, you would just define it as a design. And then very important are these manufacturing settings. So we have several hosted in ColdStream, for example, CNC milling, 3D printing, and die casting and sheet metal forming. Of course, for these cold plates, it would be sheet metal forming. And we can actually guarantee fully manufacturable designs right here. And so again, maybe let me unselect this so I can show you. If you select sheet metal, you have the different manufacturing constraints right here. For example, for sheet metal forming, you need inputs such as a RF min and max, an inner and outer bending radius, a thickness of the plate itself, a chamfer angle, and then a delta, which is the height of the actual cooling channel. So for this specific project, we created a custom one. And then you pick an orientation. So in this case, the yellow is the y-axis. And then, yeah, of course, you select a material of these actual structures. Most likely those will be the same as the stamped and the base plate. All right, so far, so good. Design region defined. Last thing to do are set the targets. So again, what the targets you can see quite conveniently where they're set with this red icon right here. And so the three things that make cold plate design so challenging are low overall temperatures, a temperature uniformity, and pressure drop. Wanting to optimize for all three of those is quite a difficult goal definition. But in ColdStream, you can actually set all of those things quite conveniently. So for the max temperature minimization, there is an objective statement there. And the way our targets work is you either have an objective function, which means it is a minimization, and you also, the other group are fixed value constraints. So if you know, for example, a certain threshold should not be overshot, you would work with a fixed value constraint, while if you're trying to get the best performance possible, you would use an objective function. All right, so in our case, we want to do multi-objective, right? And so we've selected that we want to do temperature minimization and temperature variance minimization across all four of the plates. And that's actually why we modeled them as the four modules together, because the temperature variance was supposed to obey across all four of the modules and not each of them individually. You can always give them different weightings. That's also possible. And then for the pressure side of things, we have the target defined on the inlet. And there we knew, okay, for this specific situation, for this vehicle, we have a maximum pressure loss available of 30,000 Pascal. So like I said, in this case, it's a fixed value constraint rather than another optimization objective. And we see, in our experience with cold plate design so far, we see that if you really want to maximize the heat transfer, it is better to have a fixed value constraint for the pressure loss, and then minimization objectives for the temperature. And with that, you really get you maximize heat transfer with that set of values. All right, now you can see all the necessary parts are well defined with this green check mark. And that's really all the manual engineering that you need to do when using a generative design tool like ColdStream. So the days of a CAD engineer trying to draw so many designs to finally get to a well-performing performance is not needed anymore. You just need good user input for the situation, for the cooling solution itself, and then you can let the algorithm fill a design space with a certain structure. Okay, next I would like to show you the results and what that looks like on our platform. So again, I've uploaded the tab. So right here, you can see our results in a tabular view, which is really nicely. So you can see, for example, Tmax and Tmin. You can see that what were the pressure values. So you can see of the 30,000 pascals that we said were available, 28,000 and a little bit more were utilized. You can then see what the actual flow rate was, and then also the heating power right here. So a few quick looks on some parameters, but more interestingly, you can also see the results in a 3D viewer. So here you see the cold plate that ColdStream designed. And yeah, you really get these really nice organic looking shapes and structures that simply a human engineer could not draw themselves, or it would take them a very long time to do so. So here I'd like to bring your attention to these two buttons. This is where actually you can get your step file of the structures, and then of course you can download your results as well. And so you can do a little bit of post-processing. For example, if I only enable this, you can see a temperature gradient of the cold plate itself. So that is entirely possible. All right, and with that, I will just summarize basically the benefits of generative design and the benefits of ColdStream. So as you can see, the design cycle time really reduces to only a few weeks, rather than in classical engineering several months. And the amount of manual engineering, moreover, is even less than the overall design cycle time, because setting up a case only takes a few minutes. And really the learning curve is also quite short. Once you've set up a few cases, you can be as quick as only 5 minutes. Of course, the design performance can be beyond anything a human could draw themselves. And for this plate, all the performance requirements that were necessary for temperature and pressure were met. And you don't really need to be a thermal expert to be able to use a generative design tool. And that's another great benefit, that you don't have to have a background in CFD, because the meshing is automated by the tool. And therefore the entry barrier to very high performing designs is much lower. I should mention that ColdStream is a cloud-based software, so there's no hardware investment, and you always have the latest version and access from anywhere with as many users as you want. All right, well, thank you so much for listening to my presentation. We do have time for a few more questions. I should also mention that there were a couple of moderators following closely, and hopefully they were answering some of your questions already. But I can just see if we have some that I can answer. All right. The first one, so for generative designed cold plates, what kind of performance improvements have you seen in maybe a comparative study to conventional designs? Yeah, that's actually a really great question. So we, of course, have done comparisons. So what do our designs, how do they compare to, for example, serpentine designs for cold plates or dimple structures? And we see that, you know, for on the thermal side, between 10 and 20% of performance improvement is absolutely feasible. And actually, we just released a white paper doing such a comparative study for battery cold plates. And I'll make sure to leave the, I can send you information on that white paper if you would like. All right, maybe a few more questions. Hi, Adrian. Thanks for the great presentation. I was wondering how you're able to guarantee 100% manufacturability. Yes, of course, that is a pretty big concern. Of course, in the end of the day, it's nice to have all these shapes and structures, but can they actually be mass manufactured? And so the answer is actually quite simple. Well, if your user input for the manufacturing constraints for that design region that I showed you, if those are true to what your manufacturing supplier can do with their machining and tooling, then our structures can guarantee that they're compliant with them. So it's, again, with good user input, we can deliver fully manufacturable parts for sheet metal forming or for roll bonded cold plates even. Okay, I see one more question I think that I would like to answer. So this one says, I'm trying to design a cold plate that has a more complex shape than the example you just gave. Are there any limitations on the complexity of the geometry? Yeah, that's, again, thanks for the question. That's a really great one, and the answer is no. So we have built ColdStream to be a tool that can really be super flexible. So of course we can do cold plates for electric vehicles, but the limitations on the geometry, simply put, there are none. So and the applications can then also always adapt to your geometries and to your inputs. So whether it's a cooling sleeve that's cylindrical, that can absolutely be the case. If your design regions are cylindrical or of any other shape other than, yeah, the rectangle that I just showed you, that's absolutely not a problem. There are no limitations on the input geometry or the design space itself where the optimizer is allowed to place the channels. Yeah, so no worries there. Okay, I think that concludes the time that we have for today, and I think all the questions were answered that I see. Thank you to my moderators for following along and taking care of that. So what I want to leave you with today is, well, how can you actually discover generative design yourself? Well, we have set up a Try Now account. Basically, if you follow this URL, diabatics.com/utility/try-now, you, with just an email, you will gain access to our generative design platform ColdStream, and you can have access to a few predefined cases that we have already created and finished there, and so you can explore those even today. And yeah, if you want to learn more, please don't hesitate to stay in touch with me. Feel free to shoot me an email or give me a phone call. These are my contact information right there, and we're of course happy yeah, to spread the knowledge about generative design and also see how we might be able to help you with your cold plate design or any other cooling solution that you might be developing. Okay, well, thank you so much everyone for following along and for watching today's webinar. I hope you were able to learn a thing or two about generative design and also see the ease of use and how your manual engineering hours can really be reduced and how generative design will be the design methodology of the future. Thank you so much once more, and have a good day.